is right here. Yep. Ui. Yes. Oh. Okay. I hope that everyone is ready. Good afternoon, everybody. Welcome you to SCI33205. That's the physics number 4 in for M604. We would start the first chapter right here, and I hope that you have got this file already, right? It's the it's the lecture note file, right? It's lecture notes file. I hope no one is gonna join more, right? Just according to let me see the chatting. Yes, according to our agreement, as I explained it, let me check whether the sound is right or not. Test 1 2 3 test 1 2 3 okay, test 1 2 3 test 1 2 3ครับไม่รู้ว่าเสียงไปหรือเปล่าครับเหมือนเสียงยังไม่มาครับโอเคเสียงไม่ไปเหรอที่ซูมนะครับไม่ทราบว่าได้ยินเสียงกันหรือเปล่าครับSCI yes SCI33205. I'm not sure whether you can hear me or not แต่ที่ผมเทสนี่เสียงไม่ไปนะครับมาอีกแล้วนะครับนัทชนนท์ครับ Okay, are you ready? Yes, the content David. The content in the first chapter will be in the following. The first topic that we will talk is the types of the wave. All right, we're gonna see. We're gonna see what is the how many types of the wave and what are their characteristic. The next one will be according to our agreement, you need to type or write down your name, okay, and that's the sign of your attendance to the class, whether you are in Zoom or in YouTube. All right. Yes. มาเรื่อยๆนะครับ Okay, the next topic is the production of electromagnetic wave. All right, the acronym or the abbreviation of electromagnetic will be capital E and capital M. Okay, we are gonna use this short alphabets later. The EM wave can be generated in the sense of electric field and magnetic field, right? In the third topic is the spectrum of electromagnetic wave. So we will see a different ทำไมเสียงไม่ไปนะครับเสียงไปเนาะแสดงว่าคุณพิมพ์ชื่อมาแสดงว่าเสียงไปนะครับแต่ผมไม่เข้าใจว่าทำไมผมไม่ได้ยินนะครับโอเคเดี๋ยวผมใส่อีกหูฟังหนึ่งดีกว่าครับโอเคif you join the class in Zoom you can type or write down your name in Zoom in YouTube I mean sorry yes the next topic is the polarization of electromagnetic wave. Okay, in this one, in spectrum of electromagnetic wave, we will see the different. We will see the whole picture of the electromagnetic frequency region, and it can be described in different sub-frequency bands. And human has made use of those different frequency bands for different applications, for medical treatment, for wireless communication, for remote control, and for many things. Okay, and we're gonna go into deeper detail, and we will have some calculations about how the EM wave propagates in nature. And yeah, here you would have some problems, some example to practice ourselves in calculation of how the wave propagates through different mediums. Okay, the next one is the application. Okay, these two topics will be combined together. And we will see the application of the electromagnetic waves, okay, how important we have to learn this topic, this chapter. And we will see how the human behave or use the EM wave in wireless communication. Okay, that's the whole picture for this topic, this chapter. All right, wave okay, wave types. Okay, how many types of the wave do we have in nature? Okay, the physicists or the scientists divide them into 3 different categories. Wave is disturbance. Okay, it's the fluctuation of nature size, okay, nature medium and so on, and yeah, it propagates from some place to another place, and the place that the wave is originated is called a source, and the destination the wave is propagating to is called destination or the receiver. Okay, there are three different basic types of the wave. The first one is mechanical waves. Okay, you may have already seen the mechanical wave, for example, the wave that is generated in the string and so on. In the wave that is due to the water in the sea, in the ocean, that's also mechanical wave. And what else? The voice, okay, that propagates from one place to another place through the air or through some concrete wall or through soil or something like that. Okay, human may use also sound to look for petroleum sources under the ground. Okay, and the second type of the wave that the scientist has classified to has divided into is called electromagnetic wave, which is the type of the wave here we are gonna study in this chapter. Okay, it's abbreviated by EM wave. Okay, all right. And the last one is the matter wave. Okay, this is beyond the scope of this chapter. Mechanical wave can be described well by the Newton's law. Okay, that's the classical law in physics. Okay, and the mechanical waves needs to have a medium. Okay, the substance that the wave will propagate through. Okay, example of the mechanical waves are water wave. Okay, the water surface of in any container, whether in the ocean or in any glass and so on. And sound waves are also known as mechanical waves. Okay, the voice that is propagates from my mouth or my throat to the microphone, and it's transmitted in electrical signal through the wire, and then it reaches your side in whether it's in computer, in iPad, in telephone or handy, and then the handy or the mobile phone will convert the electric signal to the sound wave again. Okay, and seismic wave is another type of wave that the people who works with the ground or the soil will try to explore something under the ground. Okay, or it's the wave or the vibration caused by earthquake and so on. Okay, there are also different there are more examples of the mechanical wave. For example, the thing that we try to bring it up and bring it down. Okay, that's the mechanical wave, and based on the oscillating direction and traveling direction in mechanical wave, we can see that in the whole in all types of mechanical wave, the wave may be classified into different manner. For example, if the wave propagates in the same way as the vibration, it's called longitudinal wave. Okay, it means the wave propagate in the same way as its traveling direction. For example, the sound. Okay, the sound or the voice here is longitudinal wave. Another type of the wave in this sense is called transverse wave. Okay, it means the oscillating direction is perpendicular to the traveling direction. So what does that mean? It means it propagates in some way, and there is vibration that is perpendicular to its propagating direction. Okay, what is the example of this one? The electromagnetic wave is classified into transverse wave. Okay, the EM wave is transverse wave. The voice or sound is longitudinal wave. All right. What else? The EM wave arises from the oscillation in electric field and magnetic field. As I told you, we are gonna study how the EM wave is generated by electric field and magnetic field. And the EM wave doesn't need any medium. The example of EM wave is gamma rays, X-ray, ultraviolet wave, visible light, infrared wave, microwave, or radio wave. Okay, you will see their applications at the end of this chapter. Okay, but at least you know different kinds of electromagnetic wave. All right, matter wave, which is spatial here in the third type of the EM wave, is known as the central part of branch of physics, and it's considered mainly in quantum mechanics. It has something to do with protons, electrons, neutrons, and other particles in nature. So this is beyond the scope of our physics college, the physics at the high school level. Okay, the medium. What is the medium? The medium is the substance that mechanical wave will propagate through. Okay, but for us, in this chapter, the EM wave doesn't need any substance or medium, because the EM wave can propagate even in deep space in vacuum without any medium. Okay, okay, they use only the vibration of electric field and magnetic field. Okay, we are gonna start with the generation of the EM wave. Okay, we start with the electric field. Okay, let's limit ourselves to the electric field. You have the positive charge source here. Okay, it's denoted by the brown one here, or the orange source here, and we have on another side the negative charge source is denoted by the violet area here, and it has negative Q. Okay, let's say they have equal amount of charge, but in a different polarity manners. So this one is positive charge, this one is negative charge. Okay, and the electric field will start from the positive charge source, and the line of the electric field will be in this way. Okay, it's not a straight line. Okay, it's a curve, and it can propagate even far away from both places, and finally the electric field will reach the negative charge area. Okay, this is what you may have seen before in different areas of physics. Okay, let's go further to go further to be close to how the electromagnetic wave is generated. Okay, at least you know that if we have a long straight copper wire like here, you may use the right hand. Okay, you may use the right hand, and the thumb finger here will represent the direction of the current. Okay, let's say we have the current flowing through this long straight copper wire, and of course everyone on the right hand side would have 4 remaining fingers, right? And if you turn your 4 fingers, okay, the direction of your remaining 4 fingers, remaining 4 fingers will represent the direction of the magnetic field. Okay, the magnetic field is vector quantity. Okay, you can see here it has also the arrow above the variable b. Okay, if we don't write down the arrow, it means we are talking about the magnitude of the magnetic field. But usually the magnetic field should have its own direction. That's why it's a vector quantity. Here your 4 fingers will represent the direction of the induced magnetic field. All right, it's going to be a circle line like this around the copper wire. Okay, but if the current is flowing from the right side to the left side, okay, it means the direction is in the opposite way. You may have to use the right hand side in a different direction as well, and the magnetic field will propagate in the opposite way as opposite way to the direction which is shown here. All right, charges in uniform motion is denoted by the current here. Okay, the current is actually the charge movement per time. Okay, if the charge stay constant like it, okay, without any movement, you have only electric field, right? But if the charge move constantly with constant speed, you're gonna have the electric field and also magnetic field, but still there is no electromagnetic wave. Yeah, still there is no EM wave. What else? Electric field and magnetic field, right? What I forget to mention. What is that? Okay, the charge that moves inside the copper wire is not the positive charge. Okay, the charge that moves in the copper wire is actually electron. Okay, electron can move from one metal atom to another metal atom, but human use a pseudo convention like I. Okay, the current, it looks like it seems that the positive charge move from the left hand side to the right hand side in the same direction as the current I here, but it's not true in nature, because the positive charge like a proton can't move from one nucleus to another nucleus. Okay, only the negative charge, which is electron, can move from one atom to another atom, but the electron moves in this way. Okay, in the opposite way to the current direction convention right here. Okay, let's move to the next one. We have different type of current movements. All right, the one here is let's say the current is moving upward. Okay, it is moving up like this. In we still need to align our time direction to the direction of the current. Sorry, and the remaining four fingers still represent the direction of the magnetic field, but this look like the 3D drawing figure, right? But here, if we draw it in two-dimensional figure in a plane like this, on the right side of the current, we're gonna use the x side, okay, or the multiplication side, you can see, to represent the rear part of the arrow. It means that the magnetic field, as you know, magnetic field is a vector quantity. It should have its own direction, right? Yes, of course. At the right side, on the right side of the long straight copper wire, we would have the magnetic field, but which direction on the 2D plane here? The x side, or the x symbol, or the multiplication side here, represent the rear part of the arrow. It means the arrow is pointing into this plane, okay, into this lecture notes plane. May I close the Zoom at the moment? So if someone want to join Zoom, I may not be able to notice your request at all, because I want to mention at our lecture note. Okay, on the right side here is the rear part of the arrow, and it means the magnetic field is pointing into this plane. Okay, once you see the x side or the multiplication side, it means the magnetic field is pointing into this paper plane. Okay, and let's take a look at the on the left hand side of this long straight copper wire, here you can see dot, right? The small circle. Okay, it looks like dot. Actually, it's only a tiny dot. The tiny dot represent the front view of the arrow. Okay, so it's like it looks like you are watching the front part of your pen. Okay, you can see only the tiny ball in front of the pen. Okay, and that's mean the front part of the arrow. So that's why we have the small dots here. And what is the meaning? What is the relation to the magnetic field? The magnetic field, according to the right hand side, will propagate out of the plane, the 2D plane here. So that's why we can see only the front part of the arrow. All right, this is the front part, this is the rear part of the arrow. The magnetic field is pointing or going out of this plane, okay, 2D plane. And here is the 3D diagram of the same thing, or the same phenomenon that you have here and here. All right. Once you use your right hand side, you can draw or write down the circular path of the magnetic field. Inside you have a small circle, and the circle is going to be bigger and bigger once you go far away from the center of the long straight copper wire. All right, and still the important thing is the arrow that represents the direction of the magnetic field. Okay, this is the 3D drawing figure. So we have the arrow that represents the magnetic field that is caused by the current moving upward like this. Okay, we need to have first the agreement whether into the drawing system whether we have the magnetic field pointing into or the magnetic field pointing out of the 2D plane. Okay, right hand rule for here is the right hand rule for determining the magnetic field direction, and in the middle the outward and inward direction of two-dimensional representation of magnetic field, and on the right figure we have three-dimensional representation of the magnetic field. Okay, let's go further in qualitative sense. Okay, in quantity sense, you have already seen how we represent the direction of the magnetic field, right? Because as I told you, the magnetic field is actually a vector quantity. So any vector quantity should have two things, right? The first one is the direction, and the second one is the magnitude, right? And on that page you have already seen how we determine the direction of the magnetic field, right? Next we are going to talk about, or we will consider the quantity of the magnetic field. Okay, let me see the time that we are going to finish for this 12:40. So we are going to finish, stop at 13:30. Okay. The way to determine the magnitude of the magnetic field is developed by these two people. The first one is Biot, and the second person is Savard. Okay, so in order to spend some dedication to them, to both of them, we are gonna say this is the Biot-Savard law. All right, this law has been developed, was developed a long time ago, and the magnitude of the magnetic field, this is the vector version, right? The magnitude will be the same thing without the arrow. Okay, that's why you have B on the left side here, left hand side. The unit of the magnetic field magnitude is Tesla. Okay, it's denoted by capital T. And in this subject, in 1 year, you're gonna see that I always use the square bracket to mention that this variable, this letter, is the unit of the quantities in physics. All right. In some lecture, with many teachers, they may not use the square bracket, but in order to differentiate the letter from variable, I'm gonna use the square bracket to mention that this is the unit of some quantities in our subject in physics. All right. Okay. Tesla is actually is derived from volt second divided by or per square meter. Okay. Meter square. All right. The magnitude of the magnetic field caused by the long straight copper wire. Of course, it depends on the location where you are, right, from the long straight copper wire. If you are close to the long straight copper wire, you will get high strength of the magnetic field. Okay, you get greater value of B. If you are far away from the center of the long straight copper wire, you are gonna get weaker or lighter amount of magnetic field, and that's called this relation has been observed by Biot and Sawat. You can see that the magnetic field magnitude is inversely proportional to the distance r. Okay, distance r is the distance between the center of the long straight copper wire to the location where you are standing to observe, where you are to observe the how much the magnetic field could you observe. Okay, could we observe? It depends also on 2 pi. Okay, 2 pi means the circumference, okay, of a circle, right? And it's not the area. Okay, it's circumference. And of course, in any experiment in science, we would need the constant, right? Because you know that the magnetic field is inversely proportional to the distance. Okay, when you are far, you will get weaker magnetic field. But one thing is that if you increase the amount of current flowing through this conductor or copper wire, you're gonna get higher amount of magnetic field. Okay, if you don't have any current flowing at all, you will not be able to observe the magnetic field. So the stronger the current here, the greater the amount of the current, the stronger the magnetic field you could observe from this experiment. So it means that the magnetic field is proportional to the current. Okay, we use the letter I to represent the current passing the wire. Okay, without through. Okay, this is wrong. Passing, flowing through, but not passing. Okay, I'm gonna move this one. Okay, remove this one. But in any size experiment, we are gonna need the constant, right? And the constant has been discovered as mu zero. Mu zero is actually, this formula is derived from something more complicated than this. Okay, it requires the calculus, the integration. Okay, but for us, it is assumed that for you at the moment you don't have enough background in calculus, so they just provide only the algebraic expression of the magnetic field. But some of you may have already read some stuff in advance, and they they show their knowledge, or your elder classmate in the last year. They show their ability by sending me the homework about the Biot-Savart law in bachelor degree level, and it involves some integration. Okay, that's fine. Okay, for me, I can understand that, but I'm gonna say something in basic level like this, because we may assume that you don't have enough background in calculus at all. Mu0 is 4 pi times 10 raised to negative 7, and the unit of mu0, even it is a constant, it has its own unit, and the unit of the mu0, which is the constant, is Tesla meter divided by ampere. Okay, ampere is the unit of the current. Yes, you know everything, right? R is the shortest distance. Okay, the distance. Okay, the distance should be measured in the straight way like this. If you are here, okay, it doesn't mean that you measure the distance like this. Okay, it's too long. Okay, the shortest distance means it should be a straight line. Okay, measure directly from the center of the copper wire to the location where you are standing. It's not any arbitrary curve like this. Okay, this one will be very long. Okay, R means the straight direction, straight way, straight line here. Yeah, in physics, okay, in the whole year for our physics, we will use the meter as the unit for any distance in physics. Okay, in this subject, it's not the same as in chemistry or in other subject. Okay, the SI unit for the distance is meter. So accelerated charges is the generation of the electromagnetic wave. Okay, when the charge is moving with a constant speed like this, constant velocity, we would not have electromagnetic wave. But if there is the acceleration, okay, if there is an acceleration of the charge, of course there will be electric field, right? Because even the charge doesn't move, we have electric field like this. And once the charge move, we have magnetic field. But one special thing is that if the charge has an acceleration, we would have also electromagnetic wave. And we will see how the electromagnetic wave is generated in the following way. Okay, at t equal to 0, let's say we capture the time, and we assume that at the beginning we have t equal to 0. And here is the long straight copper wire. All right, and this is the symbol of the alternating current voltage source. Okay, I need to introduce you to some basic notation of the electric devices. Okay, of course you know this one before, right? This is the DC direct current voltage source, right? And you have seen this one before, right? It's called AC voltage source. So what is a DC direct current? So this is time, and here is Vt. The direct current will give you a constant like this. This is DC. And for AC system, this is Vt, the voltage depending on time. The alternating current will be somehow this. Okay, it has the shape of psi. All right, and the AC voltage source is denoted by this symbol. They use the sinusoidal one period of a sinusoidal waveform to represent something inside this. Okay, and this is the altering current voltage source. Okay, let's say at time 0, the current is moving from this end to the upper end. Okay, the bottom end to the upper end. Okay, and here is the positive area. Okay, here is the negative charge area. And of course, as you know, in the first page of this lecture, the electric field will start from the positive charge area to the negative charge source, right? Yes. And yes, of course, as you know, here is the positive charge source or the positive charge area. What we can imply is that the electric field will start from the positive charge area to the negative charge area, right? That's the typical manner. And once we let the time goes a little bit by, and by one by 4 of the wavelength, the voltage source tends to decrease. Okay, it turn out to be 0. Okay, so the electric field will tend to 0 here. It means at both ends there is no negative charge area at all at the moment, and here there is no positive charge area at all. Okay, both are symmetrical, both are charge free. Okay, there is no charge. So once they don't have charge, it means we also don't have electric field. Okay, the E field. And once the time goes by, okay, here I need to write down the complete form of the actual shape of the AC. Okay, at t equal to 0, we are here, right? When t is equal to capital T by 4. Okay, capital T means the period. Okay, T represents the period. What is the period? Period means how much time the wave has propagated by one cycle. Okay, that's the meaning of period. Okay, you just use your watch or your clock to capture the time. Okay, once the wave complete its own one cycle, we're gonna say that time period is called period. Okay, T. Here T by 4, you have 0 and there is no electric field at all. And once you let the time go by further by T by 4, you will reach this point, and it means that the upper end will be full of positive charge and the lower end will be full of negative charge. And of course, in the typical manner, the electric field will be generated from the positive charge area to the negative charge area. So now the E field is pointing downward like this. Okay, at t equal to 0, we have the E field pointing upward, and it's gonna it decreases a little bit until it reaches 0, until it is equal to 0. And once you let the time goes by, another side of the copper wire will collect the opposite charge. Okay, before they have negative charge, and once the time go by, they collect the positive charge. And now the E field is pointing downwards, so that's why we have the arrow pointing down below this line. Okay, because it's negative quantity. Okay, and here is the time of t by 2 is the half of the period, because you can see that the wave has been completed by 1/2. Okay, or 1 by 2. เชิญครับหมดเวลาแล้วใช่ไหมครับ ครับขออภัยครับครับได้เลิกครับก็จบเพียงแค่นี้ครับคนไหนไม่ได้พิมพ์ชื่อโปรดพิมพ์ชื่อนะครับอย่าลืมนะครับเดี๋ยวผมเช็คชื่อนะครับขอบคุณมากครับที่แจ้งผมครับได้ครับเชิญเลยครับสวัสดีครับมีคำถามถามได้นะครับแม้จะออกไปแล้วตรงนี้นะครับใช่ไหมครับไม่ใช่ครับไอเดียวนะครับทำให้เกิดหลายๆวงครับแล้วก็ไม่ได้มีจำนวนเส้นเท่านี้เท่านั้นจริงๆจำนวนเส้นมันต่อเนื่องครับแต่ที่เขาวาดวงเพื่อให้เราดูได้ชัดเจนจะไปวาดรูปดิสที่เป็นระนาบเลยเดี๋ยวคุณจะงงครับเขาก็วาดเป็นเส้นๆขึ้นกับว่าเส้นนี้หมายถึงจุดที่คุณยืนอยู่ตรงนี้แล้วคุณสังเกตได้เส้นนี้คือจุดที่คุณยืนอยู่ตรงนี้แล้วคุณสังเกตได้ครับมันก็มีหลายจุดที่คุณจะยืนแล้วคุณสังเกตแต่จริงๆเส้นพวกนี้มันต่อเนื่องหมดครับเกิดจากไอกระแสเดียวครับไม่ได้เกิดจากหลายๆไอครับครับผมตอบคำถามคุณชัดเจนไหมครับหรือว่ายังงงอยู่ครับ ครับถ้าหมดเวลาแจ้งได้เลยนะครับไม่ต้องเกรงใจนะครับขัดจังหวะผมได้ทันทีผมจะได้หยุดครับเพราะผมไหลไปตามเนื้อหาเรื่อยๆนะครับ604จบเซสชันไว้เพียงเท่านี้นะครับ Oh no I have to close the Bluetooth, earphone, oh, wireless LAN too. Mm, 5G. No, I don't. Oops. But yeah. Let's start. We're gonna send Electromagnetic Wave to the end. Yeah, foundation, good notes, so you know, very important new thing. Open a new thing. Chapter. Item. This. And the seeds. 11. 05/2022. All right. And close it. We have translate the text. This right. Download to shadow one and assets and then the this one. Select next. Subsystem. Class attendance. Class attendance. Second semester. M604. It is days 11. Let's see. $28. should be again same. 9. Okay. Yeah. Right. Okay. Good afternoon. Everybody, welcome you to SCI. Right. Okay. Okay. Welcome you to SCI 205, and this is the section for M605, right? Okay, this is the first chapter, and it's known, the title of this chapter is Electromagnetic Waves. There are several topics in this chapter. The first one is wave types. Okay, how we classify many waves in nature into different categories. And the next one is how, because we pay attention to electromagnetic wave, right? Electromagnetic could be abbreviated by the letter E and M. Okay, EM wave. It means EM can be generated by electric field or magnetic field, right? It's the combination of electric field and magnetic field. Yeah, we will see how the EM wave is generated right here in this topic. And next one is that because the EM wave cover a broad class, different frequencies, so we would see spatial behavior of each frequency band of electromagnetic wave. You need to know the formula of C equal to lambda f, and different frequency band has its own lambda, right? Because they have the same speed, which is 3 times 10 to 8. Or that's the speed of the light, right? We will see different frequency bands of the EM wave right here in the next one is the polarization of the electromagnetic wave. Here we would have several calculations or several examples for the electromagnetic wave in we will see how the EM wave behave when it propagates through different media. In the next one, we will see the benefit or the reason why we should learn or study something about electromagnetic wave. We will see the application, right? How we use different EM wave frequency band, electromagnetic frequency bands to solve human problem like medical treatment or wireless communication, radar for airplane at the airport and so on. The next one is the communication, right? How human uses the EM wave for communication. Okay, the first topic is the types of the wave, right? As you have learned before in physics, you may have seen already the string wave, right? The wave that is caused by string once you move the string up and down. Yeah, that's also the wave. You may have already seen the water surface in the ocean or at the sea, right? And that's also a kind of wave. You may have learned that the voice or the sound from any source, that's also a kind of wave. Okay, and the physicists or the scientists have classified so many waves into three categories. What is the meaning of wave? Okay, wave is the disturbance that propagates or the fluctuation or the vibration of something that propagates or moves from the place where it was created. So it's from the source actually. So finally, the scientist has classified them into three different categories. The first one is mechanical wave. Okay, mechanical wave means the wave that requires a medium, and yeah, like the string wave, right? It requires a string. For the sound wave, we need to have the air, right? We cannot talk to each other in vacuum because there is no medium at all. What else? The sound wave and yeah. The second type of the wave is electromagnetic wave. Yeah, this type may not need the medium at all. Okay, the electromagnetic wave, for example, like the light, can be generated from any source like the sun and so on. It can start from the sun and it can start from the sun, propagate through the deep space without any air at all, and the light, which is a type of electromagnetic wave, can reach our Earth, right? The last one is matter wave. Matter wave is the wave that is beyond our lecture, our subject. It's related to tiny particle like a proton, neutron, and electron. Okay, for us in this chapter, we are gonna consider electromagnetic wave or EM wave. All right, let's talk a little bit about in order to differentiate the EM wave from other types of the wave. Let's talk about the first kind of the wave, which is mechanical wave. Okay, mechanical waves can be analyzed or can be predicted by the Newton's laws. Okay, because the molecule is quite big. The first one of the first example of the mechanical wave is water wave. The second one is the sound wave. Okay, this is what you may have already studied before in the last year or last 2 years. The last one is a seismic wave, which is a wave that is that happens during the earthquake and so on. It also includes other types of waves like the string wave that you may have seen during your Matthew 3 or something like that. Okay, the wave can not only be classified into 3 different types like mechanical wave, electromagnetic wave, and matter waves, but also can be classified into 2 propagation behavior types. The first one is called longitudinal wave, okay, and the second one is transverse wave. Okay, what is the difference between these 2 types of wave? The first one is oscillating direction. Okay, we use the oscillating direction and compare it to the traveling direction. Okay, like the sound wave. Okay, the compression of the air and the increased amount of the air will take place in the same direction as the sound propagates. So that's the longitudinal wave. Okay, that's an example of the longitudinal wave. Another type of the wave in this manner is transverse wave. What is that? The oscillating direction is perpendicular to the traveling direction. For example, the string that doesn't move at all, okay, but the string fluctuation goes up and down, right? The string, where's the pen? Like you are here and you fix the string with this, right? And you oscillate it, and you are here. You hold another end of the string, right? The string goes, let's talk about this. Okay, this point goes up and down, but it doesn't move along the direction of the wave. So in this manner, we're gonna say that this is the transverse wave. And the electromagnetic wave, which is our interest here in this chapter, what do you think? Is it longitudinal wave or transverse wave? Let you predict. Okay, one thing I didn't mention to you is that according to our agreement, you may have to write down your name, right? 605. Okay, it's sufficient to write down 605 for the first person, okay, but you don't have to write down 605 every time. Only the first person, so that I can differentiate you from the student in M604, okay. But it's fine if you all the time say 605, but I prefer your number first and then your name, okay. And if in your classroom there are 2 people that share the same name and you have different surname, you may have to write down the full name, okay. All right, yes, let's get back to our story. What do you think? EM wave is whether longitudinal wave or transverse wave? Okay, any idea about that? The EM wave is classified into transverse wave because you'll see it later. The electric field, the magnetic field have the vibration in the direction that is perpendicular to the direction of the electromagnetic wave. Okay, we'll see it later. Okay, let's go further. What is the detail of the electromagnetic wave? Okay, electromagnetic wave arises from the oscillation by electric field and magnetic field. Okay, these are 2 major components, major fields that we would need, and these EM waves don't require any medium. Okay, it's this is the spatial behavior apart from the mechanical wave. Okay, the EM wave doesn't require any medium. It can propagate even without the air. Okay, example of the EM wave that you may study in more details later are gamma rays, okay, which is a very high energy radiation, which is a high energy radiation. The second one is X-ray. Okay, we use X-ray to see the chest, right? To see what's going on in our chest, in our body, right? The next one is ultraviolet. Ultraviolet is the hidden light from the sun, right? And visible light is, of course, it can start from many from different colors of the light. And this is the range of the EM wave that could be observed by human eyes, right? Infrared region or infrared wave is the scope that is out of the region of our eyes. Okay, we cannot use our eye to detect the infrared. And next one is microwave, but infrared had its own utility, like to serve as the remote control and communication, or to kill something, okay, like a disease and so on. The next one is microwave. Okay, of course, microwave is the name that is close to a device that we use to cook some food, right, or to heat some food. Yes, microwave has actually many utilities apart from the microwave oven. Humans use microwave also for the purpose of communication. And radio wave, okay, radio wave is another region of the wave that human also uses for communication. Okay, it's has better ability to transfer the data than the microwave. Microwave is the early generation for human to communicate to each other. It's mainly used for military purpose, for the radar purpose, and so on. Okay, matter wave. Okay, the last type of the wave here is something about central part of physics, and it's known in the field of quantum mechanics. Okay, I think next semester, in the next semester, we're gonna see something about quantum mechanics. And matter wave take place due to protons, electrons, neutrons, and other tiny particles in nature. Okay, what else? Yes, okay. You may not need to write down 605 every time. Okay, only the first person that appears in the classroom. Okay, yes, medium is the substance that mechanical wave needs to use for its propagation. Okay, we are gonna start our detail of electromagnetic wave generation, how the EM wave is generated. We need to start from a very basic background in electricity. Okay, you know that if we have a charge, positive charge, and another negative charge area, there will be electric field, right? That starts from a positive charge area to the negative charge area. All right. And this behavior can be described by several lines, okay? And these lines represent electric field lines, okay? The electric field line usually start from the positive charge area to the negative charge area, okay? It has the curved V shape like this, okay? It may not be the straight line. It starts from this one to another point like this, okay? In the curvy propagation path. Okay, these electric field can happen even both charges are moving, or only a single charge is moving. But this one just stay at the same point like this. Okay, this one is just fixed, and then if this one is moving, there is still electric field, okay, that is induced or started from the positive charge area to the negative charge area like this, okay. But this is the simplest situation that we can consider. The next one is that in reality, as human has discovered the electricity, they have found the electron flow in. Human made use of electricity for many kinds of for many purposes, okay. And one of the things is that the basic situation is that if you have a long straight line like this, okay, this is the long and straight, okay, it's not curvy line, okay, of the copper wire like this. And if you let this end be connected to the positive polarity of the voltage source, and if you let this end be connected to the negative side of the voltage source, you're gonna see that the electron is moving in this way, right? But usually here when we think of something in the positive way, right? But electron is a negative charge. Human has invented the current notation. The current notation means they pay attention to the positive charge, but in fact or in nature, the positive charge inside the long straight copper wire doesn't move at all. Okay, the nucleus or the proton of the there is the handy, okay, later. The proton inside the nucleus of the metal atom cannot move, okay. For any kind of atom, as you know, the particle that can move is only electron, okay. Electron has a weak attractive force to its central part, to its nucleus, so it can be separated from the atom easily. So that's why electron is only the particle that moves in electricity, right? Human just use the pseudo convention term like the current, but actually the positive charge doesn't move at all. Only the electron, which is negative charge, okay. But anyway, we will follow this convention when they make the analysis of circuit and so on, right? We use the right hand rule, okay. Everybody has her own right hand, right? And you have the thumb direction. The first finger direction has to be aligned in the same way as the direction of the current flow, okay, the positive charge flow. But actually there is no positive charge flow. And you would have forefinger remaining, okay, like this. And if you turn around your forefinger, you will see the direction of the current. Okay, you will see the direction of your remaining four fingers will represent the direction of the B field, okay, the magnetic field. We use the B alphabet to represent the quantity about magnetic field. But one thing you need to know in physics is that we have actually two kinds of quantities, right? The first one is scalar quantity, right? There is no direction at all. The second one is the vector quantity, right? Vector quantity has not only magnitude but also direction, right? And the magnetic field is an example, is one of the vector quantities. So you can see that we usually represent the letter B together with the arrow above on top of that. And yes, of course, that's why we need to learn here how we could find the direction of the magnetic field. Okay, let's say we have here four fingers and they are going to represent the direction of the magnetic field, the B field, right? And yeah, we will talk about the quantity of the magnetic field later on the next page. But on this page, you need to have enough skill to determine the direction of the magnetic field. Okay. Yeah, your remaining four fingers will represent the direction of the induced magnetic field due to the current flow in this direction. But if the current flows in this direction, you still need to you still have to use your forefinger, but your remaining forefinger, your four remaining fingers will give you the direction of the magnetic field in the opposite way. Okay, it's going to turn around in this manner. Okay, everywhere. This circulation will take place everywhere around this long straight copper wire. Okay, charge in uniform motion. This is the charge that moves with constant speed, right? It's also known as charges in uniform motion. The charges in uniform motion will produce two things. The first one is the electric field, okay, which of course will take place all the time because you have two types of the charges. And next one is the magnetic field. Magnetic field is induced from this figure. Okay, if you have a long straight copper wire, you're gonna have magnetic field according to the right-hand rule. Okay, we have charge that stay idle. Okay, it doesn't move. Okay, this is the non-movement case of the charge, and here is the movement case of the charge but with constant velocity. We're gonna see next. Okay, later, not at the moment. Okay, we'll see it later. Here we will talk about the convention, how to the notation or the agreement, okay, in order to represent the direction of the magnetic field. All right. We have three figures: the left, the middle, and the right one. All right. Let's consider first on the left side here. We this figure, right? We consider first this figure, the left one. If we arrange the long straight copper wire in the vertical direction like this, okay, and the thumb finger will represent the direction of the current, and the remaining four fingers will represent the direction of the B field, right? The B field will turn around this long straight copper wire, okay, in this way. And this is the 3D drawing figure, and here is the 2D case. Okay. If we don't draw it in the three-dimensional system, we draw it in for simplicity in a two-dimensional plane like this. On the right side, okay, with respect to the long straight copper wire, you're gonna see that after you turn around your remaining four fingers, the magnetic field is going to point into the plane. Okay, the magnetic field is going to point into the plane, and we will represent the magnetic field in this way by using the cross sign or the multiplication sign here, the x sign. Okay, let's say for simplicity. Yeah, we will use the x sign to represent what we can see from the magnetic field in this way. The magnetic field may be considered as the arrow. Okay, the arrow you may have seen the arrow has the rear part, and here is the front part, right? Okay, this is the rear part, right? The front part. When the arrow is pointing into the plane, what we can see is only the rear part, which is the X sign or the cross symbol right here. Okay, it means the arrow that represents the direction of the magnetic field is pointing into the plane. Okay, and on the left hand side, with respect to the long straight copper wire, what you can observe after you turn around by using your right hand, what you can observe is only the front part of the arrow, and what you can see from the front part of the arrow is only a small dot here or small circle here. So if you see the dot, it means we have the vector quantity pointing to us. Okay, but if you see the cross sign or the X symbol, it means you have the rear part of the arrow pointing out of you. Okay, the arrow is going to move out of you. All right, this is the two-dimensional system for representation. Let's move to the right figure. It's the same straight long straight copper wire, okay, which is arranged in the vertical direction like this. Okay, the current is still flowing or going up, and once we draw it in three-dimensional system, three-dimensional figure, you would have your four fingers like this, and you would see that the magnetic field is going to turn around your central part, your long straight copper wire. Okay, if you are close to the long straight copper wire, you will get high or less intensity of magnetic field. What do you think? If you are close to the long straight copper wire, you would get you would be able to observe more strength of the magnetic field, right? And if you are far away from the source, which is the long straight copper wire, you will receive less amounts of magnetic field, right? That's the first relation you could imagine, right? But everywhere, okay, even we are far from the central part of the conductor or the long straight copper wire, we still have the same direction of the magnetic field, okay, according to the right hand rule. Okay, your four remaining fingers will tell you how the magnetic field is turning around. Okay, this is the magnetic field caused by the current flowing through a long thin straight wire in vertical direction. And we have the left figure here. That means the right hand rule is used to determine the magnetic field direction. In the middle figure, we have outward. Okay, the magnetic field is pointing out of the plane, and we have inward, the magnetic field is pointing into the plane. And here we have three-dimensional representation. And after we move the right hand rule, we could see that the magnetic field direction is turning around the long straight copper wire. Okay, as you have seen these two pages, okay, I think you would have enough skill to determine the direction of the magnetic field. All right. Next one is the quantity. Okay, you have seen how to find the direction. Next one is that we will try to find the quantity or the magnitude of the I think no one will try to attend the classroom, right? So let me close the Zoom so that we would better concentrate on the lecture. Okay, let's talk about the magnitude of the magnetic field, right? Because as you know, magnetic field is a vector quantity. It is described by the letter N, the arrow on top of that. Okay, here everywhere it's a vector, whether be out, be in. So in order to find the amount of the magnetic field, it's the magnitude of the magnetic field B, and it's the unit of the magnetic field is Tesla. All right, and there are two people who try to observe the strength of the magnetic field caused by the current flowing through the conductor like this. Okay, these two people are Biot and Sawat. Okay, I think both of them are French. Okay, both have studied the strength of the magnetic field caused by the current flowing through long straight copper wire. Okay, in Tesla, and due to a thin straight wire, we have a closed form expression. But actually, if you reach the bachelor, if you are in the bachelor degree, the expression for B is not simple like this. Okay, it's derived from calculus. Okay, the integration of the structure of your conductor in the place that you want to observe the magnetic field. Okay, it's represented in integral form and differential form. But at the moment, the physics college, the college physics assume that you don't have enough background regarding the calculus, so they just provide only the closed form expression for the magnetic field. But anyway, it can be easily understood. Okay, you know that if you are far away from the magnetic field, you would get weaker amount of the magnetic field, right? So it means the magnetic field B, which is the magnitude version, right? The magnetic field B should be inversely proportional to the distance, right? So if you far away from the core of the conductor, you would get weaker magnetic field. So B is proportionally is inversely proportional to the distance, which is R. And another effect is that if you let the current flow more and more, okay, with more amount of current, you would get greater amount of magnetic field too, right? So it means the magnetic field should directly depend on the amount of the current. So you can see that B depend. Let's say, okay, B is inversely proportional to the direction, to the distance. Another experiment should be easily realized that the magnetic field should depends on the current, okay, the amount of the current. So it means that B should depends on I per R, right? And there should be the constant such that I by R, okay? And the constant has been discovered as mu 0 and 2 pi, okay? Well, what is mu 0? Mu 0 is the value that these two people have manipulated, and it's equal to 4 pi times 10 raised to negative 7, and it's known as the permeability of the free space. Okay, the constant mu 0, okay, is fixed. You may have to memorize, okay, it into the brain, and the unit of this one is Tesla times meter per ampere. Okay, B is the magnitude, right? The magnitude is found by the absolute value. Okay, this is the bar, the two bars here represent the magnitude operator, okay, of this vector quantity. B is the magnitude of the magnetic field B. Okay, field B is a vector quantity, and the unit of the magnitude of the magnetic field is Tesla, or in SI version. Okay, Tesla is not SI unit, but it's a short form of several SI unit. For example, V represent the voltage, and S represent the second. That's the unit of time, right? And M represent meter, right? And that's the unit of distance. But Tesla is equal to volt second, volt times second by meter square. Okay, and it's not convenient to say all the time volt second per square meter, volt second per square meter. The guy who did something about magnetic field and is well known in the physics society is Tesla. Okay, so we dedicate our appreciation to Tesla by not saying volt second per square meter all the time. Okay, we will simply say this is Tesla. Okay, that's the same name from Nikola Tesla. You will see something about Nikola Tesla, I think, in the next chapter or something like that. Okay, yeah, and also in our subject, we are gonna say the unit of the magnetic field as Tesla. Okay, we would not say volt second per square meter. It's valid. Okay, it's also correct, but it's not convenient because it's too long. Okay, we have to spend much energy to say volt second per square meter every time. Just simply say Tesla. Okay, is a better way. Okay, I is the current, and as you know, current is the sharp movement per time, right? It's actually coulomb per second, but we will dedicate our appreciation to the person who spend so much time in his or her life to this quantity, which is the current, and we give the words A, okay, that stands from the surname by André Marie Ampère. Okay, André Marie Ampère is a French physicist, I think. Yes. We would not say coulomb per second. Okay, we will simply say ampere. Okay, but if you want to see the SI unit, it's equal to coulomb per second. All right, that's the charge per time, or simply say ampere. The distance R is the shortest distance to the Y. Okay, what does that mean, shortest? Okay, if you stay here, and you want to feel how strong the magnetic field you could receive from the current movement in this long straight copper wire. It means you have to measure the distance here directly to your location, this point. It's not the distance that you want to measure in any direction as you want, okay? The green one is not valid because it's not the shortest one, okay? The green one would have more distance than the red one. The red one is the shortest one, so this is called the distance R, okay? We will talk about this expression. Oh, no, I have to use the red color, right? So that you will not get confused. Okay, this is the distance R, okay, the shortest distance. It's not valid if you consider distance in this way, okay? It's not the long straight direct line. Okay, okay, you know something about the distance R, right? The shortest distance in meter. And yeah, we will talk about the Biot-Savart formula later, I think in the middle or in the end of this chapter. Okay, we will use it for some calculation example. Okay, you have seen the simplest case when the charge stay constant. Okay, when the charges stay constant, there is no movement. You have seen the case of charge movement in this one, right? And in this case, the velocity is constant. Okay, the speed of the charge movement is constant, is fixed, and that's the second case. The third case is that we will consider the movement of the charge once it has acceleration. Okay, the speed or the velocity of the charge movement is not constant. Okay, before we going to that scenario, I need to introduce you to basic notation. In electricity, you have here plus and minus, and this one is called direct current. Direct current water source. Okay, what is that? It means you have here Vt and T right here, and you have a constant like this, and this is the DC level. For example, if it's say 5 volt, it means it's going to have the number 5 right here. Okay, the amount of voltage this symbol will provide you. Okay, another type of the voltage source is this one. Oh no, I have to use the same color. It's this one. Okay, it's somehow like a 10 cosine 40 or something like that. Okay, you can see that it's not a constant number like number 5, right? It's 10 cosine 40, and how does it provide voltage? Well, it's equal to 0 and 1 here, like this. Okay, you can see that this notation, this one, doesn't provide a constant voltage to you. Okay, this one gives you the constant amount of voltage. Okay, 5 volts all the time, but this one can provide you a very high amount of positive volt and also negative amount of potential difference. And again, it returns to the same amount of positive voltage and returns to the negative amount of voltage later. Yeah, that's the T, right? And here is Vt. The voltage source in this manner is known as AC voltage source. Okay, and it will give you the voltage that depends on time. Okay, varies with time like this. Let's suppose the case when t is equal to 0. So we arrive at this one. Okay, at this point. So let's say the bottom end of this conductor Y. Okay, this conductor Y is driven by this AC voltage. Oh no, voltage is not like that. Okay, the AC voltage will give you at time equal to 0, like this. At the bottom end of the long state conductor, we have positive area. What does that mean? It means they try to repel every electron to this way. Okay, they try to force electron to move upward. Okay, so electron will be collected here at the upper end of this conductor. Okay, once electron are stopping here, in this area we would have mainly the negative charge, right? And when the electron is when the electrons are out of this area, we have only the nucleus of several atoms. So it is lack of electrons. So the positive charge, which is caused by proton, will exhibit the strength here. So that's why we have positive charge area in this area, and here we have negative charge area. And from what you have learned before, there will be all the time electric field from the positive charge area to the negative charge area, right? And it would also take place here. The electric field will point upward, okay, from the positive charge area to the negative charge area. And that's why we have a very high amount of electric field pointing up. And once you let the time goes by period divided by 4. What is period? Period means the time that you spend to observe the complete single cycle of the wave. Okay, you will return to the same point of the wave right here, and this time, this period is called capital T, which is known in English as period. Okay, period. All right, this is the time you spend or you wait until the wave return to its original point. And if you let the wave goes by a period by 4, you would see that the voltage reach 0. Once the voltage reach 0, it means they don't have enough ability to force electron to be here at all. Okay, electron will return to the original point, and at both ends we are in a neutral situation. Okay, everything is symmetric. Okay, there is no difference of charge at all. So once there is no positive charge area, there is no negative charge area, we are gonna have we're gonna have 0 electric field. So that's why the E field now, the amount of electric field, which is a kind of vector quantity, actually will reach 0 here. But I think now the time is over, right? We in period 9, 15, 10 to 16, right? So ต้องการให้ผมพูดต่อไปเรื่อยๆไหมครับหรือว่าจะจบคลาสเลิกคลาสเลยจริงๆควรจบตั้งแต่ก่อน16แล้วเนาะต้องเป็น15:50เนาะแต่ว่าถึงจบเลยนะครับโอเคงั้นก็ ครับจบนะครับเดี๋ยวเรามาต่อรูปนี้กันครั้งหน้านะครับเนื่องจากว่าเขาชดเชยนะมันก็เลยจะคาบสั้นๆครับแต่จริงๆ2คาบติดจะยาวไปเรื่อยๆนะครับก็ขออภัยด้วยนะครับพบกันมาสู่ครับ see you on Friday there is no homework okay please don't forget to write down your name in the chat box of the Zoom okay otherwise you're gonna get the status of missing the class okay alright see you on Friday morning bye bye ครับสวัสดีครับครับเชิญครับคำถามครับส่งไมค์ได้ครับได้เชิญครับตามสบายเลยครับผมยังไม่ปิดคลาสครับรอคุณสัก5 นาที 10 นาทีครับตามสบายเลยครับ see you on Friday สวัสดีครับบ๊ายบายครับand then to right 19 and 2 6 0 5 11 11 20 right เฉลิมธรรม20 and 29 and 29 and then 25 19 10 6 รัชนนท์7 16 17 11 13 and 8 like 14 2 and then 21 number 9 23 22 Shawakon number 1 right and Shawakon then Akira 15 24 Pumich 26 people 12 Visapon 19 Wasin Pichak number 5 yes Pon ครับ teacher I have some question yes please say teacher I have some comment yes say ปอนครับปอนพูดเลยครับเป็นไรครับไม่เคลียร์ตรงไหนผมอธิบายไม่ดีตรงไหนบอกครับ 5 and then 3 นนภัทร and then 18ผมได้ยินคุณหรือเปล่าคุณได้ยินผมไหมครับนนปอนครับปอนmy god oh what happened oh my godปอนครับปอนฮัลโหลครับเชิญครับได้ครับเชิญครับผมอธิบายไม่รู้เรื่องตรงไหนเชิญเลยครับถามได้เลยครับรูปไหนครับเดี๋ยวผมแชร์หน้าจอก่อนเนาะบิลเชมได้ครับ3แท่งป่ะเดี๋ยวผมแชร์หน้าจอคุณชี้เลยครับรูปไหนครับรูปขวาสุดนี้นะครับนี่นะตรงนี้นะครับต้องการภาษายังไงครับเอาภาษาอะไรครับเอาภาษาไทยโอเคได้ครับก็คือมันเป็นคือคุณต้องมา2รูปนี้ก่อนเนาะรูปนี้คือเราใช้กดมือขวาใช่ไหมครับอันนี้น่าจะรู้เรื่องเนาะเอานิ้วโป้งแทนทิศของกระแสที่มันไหลในเส้นลวดตรงๆนะครับแล้ว4นิ้วที่เหลือที่มันวนอ้อมตัวเส้นลวดตรงจะแสดงถึงทิศของสนามแม่เหล็กที่มันเหนี่ยวนำโอเคไหมมีกระแสไหลขึ้นก่อนปรากฏการณ์นี้เกิดขึ้นก่อนนะครับแล้วสนามไฟฟ้าสนามแม่เหล็ก B field สนาม B เนี่ยจะเหนี่ยวนำเกิดขึ้นในภายหลังโอเคไหมมันต้องมีกระแสไหลก่อนไม่ใช่มีสนามแม่เหล็กแล้วมันจะเกิดไอไม่ใช่นะมันต้องเกิดไอก่อนปล่อยให้กระแสไหลคงที่นะครับแล้วจะเกิดสนามแม่เหล็ก B เหนี่ยวนำโดยอัตโนมัตินะธรรมชาติมันเกิดขึ้นอย่างนี้ก็ต้องขอบคุณนักฟิสิกส์เขาค้นพบนะครับแล้วทุกวันนี้มันก็ยังเป็นอย่างนี้อยู่นะครับเห็นไหมพอกระแสไหลปุ๊บมันจะเหนี่ยวนำทำให้เกิดสนามแม่เหล็กหมุนรอบตรงนี้นะครับแล้วครบรอบวนอยู่อย่างเงี้ยตลอดเวลาถ้าคุณตราบใดที่คุณยังมีปล่อยให้มีกระแสไหลผ่านเส้นลวดนี้ตลอดเวลาหรือเส้นสายไฟฟ้าที่บ้านคุณนะครับถ้าคุณมีเครื่องวัดสนามแม่เหล็กไปวัดคุณจะพบว่ามีสนามแม่เหล็กอยู่ใกล้ๆกับตรงสายไฟฟ้าที่ลากในบ้านคุณครับหรือว่าที่ใดก็ตามโอเคไหมครับส่วนทิศที่มันวนนี้นะครับก็จะต่อเนื่องนะแต่จริงๆมันต่อเนื่องนะครับเขาวาดเป็นเส้นๆเพื่อให้คุณเห็นว่าอยู่บริเวณใกล้วงมันก็จะเล็กนะครับอยู่บริเวณห่างออกมาวงก็จะโตขึ้นใหญ่ขึ้นนะครับพออยู่ไกลออกมาวงกลมนะครับแต่มันวาด2มิติมันจะเป็นรูปวงรีเนาะจริงๆมันเป็นวงกลมนะอ้อมเส้นลวดเนี่ยคุณอยู่ไกลออกมาวงก็จะโตขึ้นนะครับนี่คือรูปที่แสดงวาดแบบเป็น3มิตินะครับจุดประสงค์คือให้นักเรียนนะครับให้คุณเนี่ยสามารถหาทิศทางของสนามแม่เหล็กให้ได้ก่อนนะครับว่ามันวนแบบไหนนะครับมันมีวนแบบม้วนกลับไปทางนี้ก็ได้กับวนแบบนี้นะครับวิธีที่ถูกต้องก็คือใช้กดมือขวาใช่ไหมนิ้วโป้งชี้ขึ้นไปตามทิศกระแสแล้วก็4นิ้วที่เหลือจะแสดงทิศของสนามแม่เหล็กนะครับก็ประมาณนี้ครับแล้วก็เรื่องระยะทางก็คือต้องวัดแบบเส้นตรงจากจุดศูนย์กลางของเส้นลวดมาถึงจุดที่คุณจะสังเกตนะครับอันนี้จะว่าเรื่องกันสูตรของบิโอสวาดละว่าจะหาคือปริมาณเวกเตอร์เราต้องทราบ2อย่างใช่ไหมคือทิศทางคุณหาจากกดมือขวาได้แล้วส่วนปริมาณนะครับหรือว่าแมกนิจูดขนาดเนี่ยคุณจะหาโดยใช้สมการที่1เรียกว่ากฎของนายบิโอแอนด์สวาดครับซึ่งก็เป็นไปตามสูตรนี้นะครับก็ประมาณนั้นครับโอเค
อันนี้พาคุณหาทิศทางก่อนครับรูปทางขวาครับไม่เคลียร์ตรงไหนอีกไหมครับอะไรนะครับผมได้ยินไม่ชัดครับขออภัยครับคลื่นยังไม่มีครับสีเขียวไม่ใช่สีเขียวผมแค่วาดขึ้นมาว่าเวลาเขาวัด r อันนี้สีเขียวไม่มีนะเวลาเขาวัด r ระยะห่างที่จะใช้แทนในสูตรเนี้ย r หรือว่า radius เนี่ยต้องเป็นระยะทางที่สั้นที่สุดหมายความว่าระยะทางที่สั้นที่สุดก็คือเราต้องวัดตรงๆจากจุดศูนย์กลางถึงจุดที่คุณอยู่ที่คุณอยากสังเกตเราไปวัดแบบเฉยเฉยยังไปคดมาแบบสีเขียวไม่ได้ครับเพราะว่าเส้นสีเขียวถ้าดึงให้มันตึงมันจะยาวกว่าเส้นสีแดงใช่ไหมครับมันไม่ใช่ระยะทางได้ที่สุดเราห้ามวัด r แบบเส้นสีเขียวเพื่อใช้แทนในสูตรนี้ครับ r ต้องวัดตรงๆจากจุดศูนย์กลางของเส้นลวดสีเทานี้มาถึงจุดที่คุณอยากสังเกตเอาไม้บรรทัดวัดลากดึงให้ตรงเนี้ยนั่นคือระยะทางสั้นสุดเวฟยังไม่เกิดขึ้นครับตัวสนามแม่เหล็กคลื่นแม่เหล็กไฟฟ้ายังไม่เกิดขึ้นคือคลื่นแม่เหล็กไฟฟ้าจะเกิดขึ้นสถานการณ์นี้เมื่อชาร์จเมื่อประจุมันวิ่งแบบมีความเร่งตรงนี้ยังไม่มีสนามแม่เหล็กเกิดขึ้นยังไม่เกิดขึ้นแม่เหล็กไฟฟ้ามีสนามแม่เหล็กเกิดขึ้นแต่ว่ายังไม่มีคลื่นครับเพราะว่ากระแสมันไหลขึ้นอย่างสม่ำเสมอมันไหลแบบคงตัวเช่น3 แอมแปร์มันก็ไหลอย่างเงี้ย3 คูลอมต่อวินาทีตลอดเวลาวิ่งไป3 คูลอมต่อวินาทีตลอดเวลามันไม่มีความเร่งของประจุที่มันเคลื่อนที่นะครับมันก็ยังไม่มีคลื่นแม่เหล็กไฟฟ้านะครับคือถามว่าเคลื่อนที่ไหมมันเคลื่อนที่แต่ความเร็วมันคงที่โอเคไหมความเร็วคงที่ทางฟิสิกส์ก็เรียกว่ามันไม่มีความเร่งใช่ไหมเพราะว่ามีความเร่งยังไม่เกิดคลื่นแม่เหล็กไฟฟ้าครับมีแต่สนามแม่เหล็กแล้วก็มีแค่สนามไฟฟ้าแต่ว่าคลื่นแม่เหล็กไฟฟ้าจะเกิดขึ้นได้ก็ต่อเมื่อประจุเคลื่อนที่แบบมีความเร่งครับเนี่ยชาร์จmove with acceleration ซึ่งเป็นเรื่องอันเนี้ยก็คือประจุวิ่งกลับไปกลับมาเนี่ยไอสนามไฟฟ้าวิ่งกลับไปกลับมาเพราะมันประจุอิเล็กตรอนวิ่งขึ้นไปบ้างเดี๋ยวครั้งหน้านะครับมันจะลงมาอยู่ข้างล่างเนี้ยวิ่งกลับไปกลับมาเนี่ยมันคือความเร่งแล้วเพราะว่าความเร่งมันไม่ใช่แค่ความเร็วเปลี่ยนมันเป็นทิศทางเปลี่ยนด้วยนะพอทิศทางเปลี่ยนความมันก็ก่อให้เกิดความเร่งใช่ไหมกลับไปกลับมาเนี่ยพอ e สั่นไปสั่นมานะครับมันก็จะเหนี่ยวนำให้เกิดสนามแม่เหล็กในขั้นตอนถัดไปนะครับเนี่ยมันจะก่อให้เกิดสนามแม่เหล็กตรงนี้ขึ้นมาเนี่ยพอมีสนามไฟฟ้าและสนามแม่เหล็กเหนี่ยวนำกันตลอดเวลาทีนี้มันจะก่อให้เกิดคลื่นแม่เหล็กไฟฟ้าวิ่งใช่ไหมครับตรงจังหวะที่คุณเห็นอยู่นี้ไม่มีคลื่นแม่เหล็กไฟฟ้านะครับผมวาดรูปสีเขียวนี้ไม่ได้หมายถึงคลื่นแม่เหล็กไฟฟ้านะผมวาดรูปสีเขียวหมายถึงว่าคุณห้ามวัดแบบเฉยๆโอเคไหมครับคุณต้องวัด r แบบตรงๆเป็นเส้นตรงแบบนี้เท่านั้นโอเคไหมเชิญครับปอนครับผมอธิบายทำให้คุณงงไหมครับมีจุดใดอีกไหมครับที่ยังไม่เคลียร์ครับเชิญถามได้เลยครับไม่มีปัญหาครับใช่ครับนั่นแหละคือหัวใจความเร่งถ้าตามของถ้าตามหลักของฟิสิกส์แล้วครับคุณอย่างเช่นยังไงดีคุณจากบ้านคุณวิ่งไปอนุสาวรีย์ชัยคุณอาจจะไปด้วยความเร็วคงที่ก็ได้นะคุณวิ่งด้วยคุณเดินทางด้วยความเร็วคงที่แต่เมื่อคุณไปถึงอนุสาวรีย์ชัยคุณกลับตัวเดินทางกลับบ้านทันทีด้วยความเร็วคงที่แต่ว่าช่วงที่คุณกลับตัวคุณเปลี่ยนทิศทางมันจะทำให้เกิดความเร่งเพราะว่าคุณต้องหยุดนะบริเวณอนุสาวรีย์ชัยแล้วหันหน้ามาอีกทางนึงช่วงนั้นแหละที่ทำให้เกิดความเร่งครับพอคุณเปลี่ยนทิศทางคุณจะเกิดความเร่งเช่นเดียวกันประจุวิ่งกลับไปกลับมาตรงเส้นลวดอันเนี้ยนะครับมันหันกลับทางมันก็จะเกิดความเร่งพอเกิดความเร่งมันก็จะเกิดขึ้นแม่เหล็กไฟฟ้าแล้วครับทีนี้แต่ว่าอันเนี้ยกระแสมันไหลตลอดเวลาเหมือนกับน้ำไหลเราปล่อยให้น้ำไหลผ่านสายยางตลอดเวลาไหลขึ้นข้างบนตลอดเวลาอันนั้น เป็นระยะเวลาแบบอนันต์ไหลขึ้นตลอดเวลามันไม่มีการกลับของน้ำไหลกลับของน้ำที่จะไหลย้อนสวนในสายยางมันก็ไม่มีความเร่งเพราะไม่มีความเร่งมีแค่สนามแม่เหล็กที่หมุนติ้วๆตลอดเวลากับสนามไฟฟ้าเนื่องจากชาร์จมันก่อให้เกิดสนามไฟฟ้าตามรูปนี้ใช่ไหมมีประจุบวกประจุลบจะมีสนามไฟฟ้านะครับโอเคไหมมันก็มีแค่นี้ครับแต่ว่าถ้าเมื่อไรคุณปล่อยให้ประจุวิ่งกลับไปกลับมามันเกิดความเร่งมันก็จะก่อให้เกิดสนามแม่เหล็กแล้วทีนี้ซึ่งอธิบายในครั้งหน้าครับครับเชิญครับมีอันใดงงสงสัยอยู่ไหมครับโอเคครับครับอย่าลืมพิมพ์ชื่อนะครับปอนนะครับโอเคครับพบกันครั้งหน้านะครับเดี๋ยวขออนุญาตเก็บคะแนนเข้าเรียนให้คุณก่อนนะครับครับครับเชิญครับโอ้นี่แชท18 18 18 number 3 yes oh no yeah 11 11 oh4 there is no print from him we have to close the yes and